today, so I thought we might get started. I'm welcoming everyone here today, a nice day, and it's a sacrifice to get out of the sun and get in here, but I'm glad that you're all here. Okay. Yeah, it went down. Do we have a signal? There we go. The agenda probably looks pretty common to our meetings, and we'll get right into the financial report. Again, we are solvent for another month. As we move into the new lab, obviously we have approval for spending quite a bit of money on equipment to outfit that lab. So those balances will come down, but we are solvent at this point. Our membership, that's unbelievable, actually. Over 1,800. I don't think in our wildest imagination we thought we would be over 1,800, but we are. Now, keeping in mind on July 1, that number will fall considerably. The difference represents people whose computers are still working. I'd like to introduce John Sterling to handle the nomination for new officers.
June is the last month for early renewal, but it's also the month that we do the election of new officers. These are the candidates that we've identified so far. For President, Frank Geister. Frank, you want to stand up?
Oh my goodness. Frank.
And Frank has been Vice President for the last 2 years. For Vice President, Dave Ruby. Dave, you back there? Stand up. He's busy collecting money. We won't interrupt him. Dave has been secretary for the last year. For Secretary Molly Frithioff, Molly, there she is. Molly's the one that does the updates on all of our computers. Any Monday morning, come into the lab, you'll see Molly there, unfreezing the computers, doing the updates and so on. So she's the expert on that, and she's going to be running for secretary. For treasurer, Howie, there he is. And Howie's been treasurer for a number of years. Now, are there any nominations from the floor? Come on, we'd like to get a few more people so we can have an election. Okay, not seeing any further nominations. All those in favor of this slate of candidates say aye. Aye. And those opposed? They're all elected. Now, I've got one more item I'd like to cover. The computer crooks are really rampant lately. We've got 3 computers. 4. Oh, we got another one. I just heard. We have 4 computers in the lab right now where somebody has either called on the phone, and these are random calls, they don't know anything about your computer, and they say, we understand your computer is running slow, but we have some technicians here that are Microsoft trained that can fix this for you. And they'll do it for $100 or $200 or $300, depending on which guy calls you. The other thing that happens is you'll get a thing pop up on your screen that says your computer is infected with a number of malware pieces, and we could clean it for you. Call this number, and same thing, they'll charge you. Now, when you pick up the phone and somebody says, we understand that your computer is running slow. If you hear the word slow, you did not hang up fast enough. There is no way when somebody calls you on the phone that they can know anything about your computer and there's no way that Microsoft will ever contact you by phone. So absolutely do not respond to these, just hang up. And when you see a telephone number come up on the screen, ignore that altogether. If it's still messing up your computer, turn it off and bring it in. We can get that back off. But once these idiots have gotten into your computer and made changes, it's almost impossible. I see Ken sitting here shaking his head. He's got one back there
I
that's...
fixed it.
These things take hours and hours and hours to fix. They do some really serious damage to your computer. So do not let somebody try to fix your computer. The other thing that we're seeing in the lab, people are downloading software. If you see some free software you'd like to get, like Malwarebytes or Startup Inspector or one of those programs, unless you consider yourself a real expert with computer, do not do a free download. In the last 3 or 4 years, they've been very devious in the way they download. They download other things with it. For example, on Malwarebytes, when you see a line on there that says, would you like the free trial version? The answer to that is no. The trial version means you're going to have it for 30 days, and at the end of 30 days, you can't load Malwarebytes back on there again. So if you need to download some software, come into the lab. We have most of those programs available in the lab on the network or on a thumb drive. We can load those on your computer for you. But downloading them off the internet is very dangerous.
Thank you, John. Moving on. We're into the final stretch. This is kind of like the horse race this afternoon. You've got till the end of the month to renew your dues at $5. And July 1, the reduced rate drops back to the $25 normal rate. So I really encourage you to come in the lab. Fellows are back there now to sign up today if you'd like to, but please take advantage of that offer. It's probably the best deal in town. Monthly newsletter. How many of you like the monthly newsletter? That's a real accomplishment by Jim Nelson and his team. They've done a great job on it. We're getting a lot of compliments on it, but we need your help. Those that contribute to the newsletter with points and tips and things like that, we're running out of ideas, and we really would like ideas from the membership, help on that in terms of, even if you don't have the idea developed, if you can give Jim an indication of a topic that would be worthy of looking into, they can develop it further and put it in the newsletter. But things that are important to you are important to all the members. So if it's important to you, send Jim an email, and we'll pick it up from there. Well, you've all heard that we're moving. It looks to me at this point, from all the discussions we've had, that the target date will be August. The process will be that they will remodel our lab, our existing lab first, then move us into the new lab. So we anticipate being down, as far as the lab is concerned, for probably the better part of the month of August. So make sure your computers break in July and you get them fixed before that date, or make sure they run till September. But either way, the month of August looks like we will probably be down a substantial portion of that time. Community Matters, a Board of Directors meeting, Committee of the Whole meeting. I'd also like to announce, many of you I'm sure are aware, that board member Gene Rose has resigned due to health issues, and we all wish Gene the best in his endeavors to restore his health. Okay. Also, a community item that we wanted to mention. For some time, this has come up with Sun City and with a number of things about getting rid of prescription drugs that you have. And for a number of reasons, legal reasons and what have you, Centegra, the association, simply is not in a position to do that. But Huntley Police Department has announced a program now where you'll be able to take prescription drugs, pills, and things of that nature to them for disposal. And so this is a program you may want to take advantage of. There's more details on the Huntley website, but essentially it's going to be Monday through Friday from 8 till 5. There will be a drop-off point. I believe, if I'm not mistaken, I think there's going to be a police officer next to that to make sure that you drop the proper things off and that sort of thing. But you're not putting your name or anything like that on. It's just disposal in a safe manner for excess prescriptions. Okay. Another thing that's coming up shortly will be the community census. I know we've talked of this before. Just want to emphasize, there's a lot of comment back and forth on this. This is very important to the association. And it's something that's required by Illinois law. If we're to retain our status as a over 55 community, we have to establish that we are over 55. And there are parameters that we have to meet, and we have to verify that. And that's a very important thing, because otherwise the entire complexion of this community would change if it became just another subdivision with all kinds of people, not necessarily good or bad, but just age differences that would be intermingled within the community. So it's very important that everybody cooperate with the association in terms of this census that's coming up. Oops. And with that, I would like to introduce Joe Quinn. Joe Quinn. Back up.
I don't know what happened to the picture here, but it was a nice picture. It was a nice picture of Fermi Lab. But anyway, in the picture, when you probably see it at home, it has some hyperlinks on it, and I put it there because it explains a lot about Fermi Labs. A lot of people here ask me, what is Fermi Labs, and I find that hard to believe because I haven't lived here all my life and I know what they are. It's a very interesting community. If you haven't been there, and I understand it's a bus trip on Monday with 2 buses, it's a research center that's very open and very community oriented. If you have grandchildren, it's a great place to bring them, particularly if they have any leaning towards science of any type, physics, nanotechnology, any of that stuff. I would highly recommend that if you get a chance to take a visit there and do that. Having said that, the speaker today is from Fermi Labs, just showing their outreach type of program, and she's going to talk about computing of science, discovery of Fermi Labs. And I would like to introduce Ruth Portis, please.
I'm just going to check the mic. Yes, so that mic is working. I've got my physics crib sheets. In case there are physics questions, I'm going to read from Wikipedia. I don't think I have all the physics crib sheets I might need. So what do? I just press this and it goes, okay, fine, there's my first slide. I'm going to talk a bit about Fermilab itself, and then I'm going to talk about the scientific computing there, of course. There's lots of computing at Fermilab, doing the traditional things like payroll, making sure we all get our checks to take home, and the procurement systems is a very big piece, but I'm going to talk about the piece of computing that is towards the scientific program and the scientific discovery that the researchers at Fermilab are involved in. So this is a picture of the high-rise. Letters to that big building in Batavia, get there, Illinois, because it's the only high-rise around in a whole set of prairies. It has about 1,700 staff and a very large site. That lake is actually not quite as big as it seems to show in that picture, but we do have a lot of wildlife with foxes and deer and herons. In the spring you see lots of white herons on the trees. About 250 of the 1,700 employees are scientists, there are engineers, computing professionals, and accelerator people. There's various accelerators on site, but the people at Fermilab work on accelerators and experiments around the world. Joe said if you have grandchildren who are into science or nanotechnology, if they're into computers, computer science, it's also a place that's very interesting for them. We have a lot of visitors, so it's an international laboratory. There are flags at the front of the high-rise showing all the different countries that come there, and users who both use Fermilab while they sit at their local institutions, and I'll talk about that a bit more later, but also come to Fermilab to do the experiments. And as I said, it's a park-like site, which, as Joe said, is very open, and people can come in and take walks and bring their kids and stuff. And in fact, for the annual open day, which is like a Sunday in March, we get over 2,000 people coming. I'm pretty impressed by how many people come to the computing club here. So actually. So I'm actually deputy head of the scientific computing division. I've worked in computing since I got a degree in Oxford, England, in 1970. So then both my husband and I are physicists, and he came to the States to do his PhD, and I came to put him through, and that's when then we arrived there, and I went and worked actually on computing in Boston. And I worked on the first colliding particle accelerator doing the computing there, and my first computing job actually was to make sure the program went from midnight to 1 minute past midnight and reset when it went past that very difficult boundary back in the 70s. We were at Fermilab for 2 years in the 70s because my husband's experiment was there, and there was the first big supercomputer that came, and it went, and the high-rise was just being built, and we all had to sit on the floor, and then they had to hoist this big CDC computer through the window for us to start using. We then went back to Europe for a few years. He finished his PhD at Oxford. We went to the big particle accelerator in Switzerland, and in Geneva at CERN, which is very much in the news at the moment. It's got very popular. One of the top BBC articles this week was the Large Hadron Collider turns on the data tap again. Right? I don't think 10 years ago, every time we turned on an accelerator, you'd see it as a top BBC news item, but it's really got the public's attention. And my sister, who's a social worker in Manchester, England, is saying, oh, well, what's happened? It's turned on. What's happened? So she's following it closely. And then I came back to Fermilab with Stephen. We immigrated. And I actually was the person who brought the World Wide Web to Fermilab in 91 or 90. I worked with, who's now Sir Tim Berners-Lee, on a completely different project to do with standard software for electronics for high-energy physics. So I met him through that, but in parallel he was working on his ideas for sharing things over the network. And in fact, Fermilab offered him a job back in 1990, and we said he could work maybe 50% on the web, and the other 50% he should work on the procurement systems. And for some reason he didn't accept the job, went on to do other things. Anyway, so basically, most of my work since then has actually been helping, coordinating, facilitating, project managing cross-discipline projects for computing and physics. So the first big one was to have a shared computing system to actually acquire the data from the accelerator in what we call data acquisition systems. And so the director told the experiments back in like 93, if you want beam from the accelerator, we don't have enough effort to do software for each experiment independently, you've got to collaborate on one system, and if you don't, we're not giving you beam. So, you know, they did buy into it for some reason. And so I was coordinating that. Then I was very fortunate. Fermilab is mainly a particle physics lab, and was purely a particle physics lab, looking at you know, very small particles and generating them in the accelerator and colliding them, or colliding them with each other, or colliding them into pieces of metal or deuterium or gas, something like that. But we did extend our scope to work on astrophysics experiments, and the Sloan Digital Sky Survey is one of the most successful astrophysics experiments in the past 20 years. They did think that they could do all the software and computing with, you know, like 3 people for 3 months, and didn't actually put any money in for anything more than that. And so Fermilab came to join, and we started to work on the data analysis systems. So this was an extension that was quite fun. Then, having done that, I worked on the joint offline computing of data processing for the Tevatron experiments. The Tevatron was the biggest collider in the world at that time. At Fermilab, it closed down about 3 years ago, and now we're repurposing the accelerator at Fermilab to work on new physics. And I've been working on distributed computing projects since the beginning of this century. That have been spanning the Department of Energy and the National Science Foundation. So Fermilab is a Department of Energy funded lab. It's one of the nation's laboratories, research laboratories. But because lots of the universities, of course, have the researchers and the students who are actually doing the physics to find the discoveries and working on the experiments of the accelerators at Fermilab and Switzerland and other places, it's very important to have software and computing that can work both across Fermilab universities, across the Department of Energy and the National Science Foundation. So we were very fortunate to be one of the Open Science Grid, and I'd like to talk about that a bit later if I have some time, is a project that's directly funded by both agencies to do computing. And now, well, actually, I'm in phased retirement, which means that I get to work 3 days out of 5, and I thought I was going to have all this free time. I mean, you've all been there. And I'm actually interim project manager of Liquid Argon software project. And this is actually quite a unique project in that usually, while experiments have agreed to use infrastructure software, like getting the data from A to B, or putting the data onto magnetic tape, or writing the output to a screen on the web, or building their software from all the different physics and scientific algorithms they've written. The experiments are quite protective of their scientific software and their scientific algorithms. While it's open software, it's very difficult to use, or for some other experiment to adopt it. But this, in Liquid Argon, which is a new detector technology that's being used for neutrinos and for dark matter, the experiments are prepared to share their physics codes, and I'm project manager to try and encourage them to do this. Okay, so Fermilab and particle physics. This is why we're funded by the DOE, is to do research. It's to find out what matter is made of, what the universe is made of. Is the universe going to expand forever? Is it going to oscillate? Are there multi-universes? And so these are sort of specifics within that search for matter that justifies our existence for the next 20 years. So the Higgs boson is a fundamental particle found at the Large Hadron Collider at CERN, although maybe we did find it at the Tevatron when you go back and look. That was discovered at CERN last year, 2 years ago maybe now, but we don't know very much about it. We don't know whether there's 1 kind or 10 kinds, like, you know, neutrinos, there's 4 or 5 of them, and so we're going to find out more about what matter is made of. And the Higgs is something that is the glue that keeps all these particles together to make the quarks, to make the atoms that make our tables and chairs. We want to look at the physics associated with neutrino masses. So the neutrinos are these particles that come from the atmosphere that have Well, we thought they had no mass, now we think they have a little mass. We thought there was one kind, well, now we know that there are, several kinds. And also they turn into each other. So if you let a neutrino travel through the Earth or they go through the Earth for hundreds of miles, and I'll show you experiments that take advantage of that, they turn into each other, they oscillate. We need to understand why and what. We need to understand the physics of dark matter. I'll talk a bit about dark matter, dark energy in some of the experiments later on. Cosmic acceleration, as I said, the universe going out and in or not, and things we never knew about before. And one, I don't know, probably a lot of you people know that 30 or 40 years ago when I started my career, there wasn't such a thing as dark energy and dark matter, and we thought we understood all the universe and all the matter in it. And now, 60 to 70 to 80% of the universe is made up of dark matter and dark energy. And depending on which unit you use, it's either 60% or 80%. So, it's really fundamental change in the last decades of saying we don't understand the universe that we're living in. And so we try to find out more about it. So this is what I said. Fermilab, which till like 2010, maybe 2012, our biggest project, our main thing was the Tevatron, where we had protons and antiprotons colliding, and we saw what's come out, and we discovered new particles called things like top and bottom and strange and beauty, but these are just glitzy names, they don't have any fundamental meaning. And then it closed down, and Switzerland became the top laboratory to do those kind of things. They actually collide protons with protons. It's slightly different. But anyway, we've now reconstituted ourselves, rebranded ourselves as the neutrino laboratory of the world. So our main thrust of the things that we do at Fermilab and the experiments we're going to build up and the extensions to the accelerator that we're going to do are towards finding out more about this neutrino, which is not supposed to have mass, but it does. We don't know why, and it may, give us the reason why there isn't an equal amount of antimatter and matter in the universe. So of course, if there was an equal amount that would annihilate and we wouldn't have anything. So we're jolly lucky that there's a surplus of matter, so we can all be here. It's sort of amazing, really. But the question is, why is that? So, there's explanations like there's another universe where everything is antimatter and we all have our anti-people there and our anti-things. Or there could be something in the way the neutrino interacts with matter and the origins of the universe that can explain that. I'm not quite sure. So one of the ways of detecting neutrinos, they're very, very difficult to detect, is you can have these big, big, big vats and spheres filled with liquid, and then you have scintillator detectors sitting around. So this is actually a picture of the experiment that does that in Japan. Of course, hydrophysics is international. There are accelerators and experiments in many different places, and this is in Japan. It all needs computing. I'll get to computing. So what we're doing in Fermilab now is our big new experiment is called the Deep Underground Neutrino Experiment, which has a very nice acronym called DUNE, and there's lots of pictures that people show. I'm not someone who makes jokes, so I'm not showing all these pictures of warriors and Star Trek and things like that associated with it. But we're actually going to send a beam of neutrinos from Fermilab through the Earth, so Fermilab's over there on the right, through the Earth, and you have to take advantage of the curvature of the Earth, to South Dakota. So the Sanford Underground Research Facility is a mine that is no longer used in South Dakota, and you can go down very far and build your laboratory, and then, because what you want to do is stop all this crud that's coming from the universe, all the cosmic rays and the things coming, you want to have as clean a beam as possible. In fact, my husband is a physicist, which is why we're here in the States. He works on looking for dark matter, or WIMPs. And he actually uses liquid argon technology, which is you take argon gas and you make it very cold, you make it as close to 0 Kelvin as you can, so he does a lot of plumbing. that's why it's a plumbing lab, the Fermilab, and they've taken this big vat, and he's actually in Italy today, under a mountain outside Rome, trying to find WIMPs. And this is where some of the other neutrino experiments have been. There was a big hoopla in the press last year about an experiment that found that neutrino was going faster than the speed of light. And of course, this is a huge, be a huge deal, because the speed of light is fundamental and nothing can go faster than it. So in fact, all the physicists said, oh, that can't possibly be true. They found out that a cable was connected incorrectly, and it was giving them the wrong timing by enough so that they thought the neutrinos were going faster than the speed of light. So unfortunately, it wasn't true. Unfortunately, I would say, is because if you overturn all the understanding of nature that we have today, then we hope the governments will give us lots more money to do research to find out what's really true. So I mean, it's a bit of a strange use of unfortunately. Anyway, so DUNE and the Long Baseline Neutrino Facility, and also experiments not in South Dakota but locally at Fermilab, are the big thing for Fermilab over the next 20 years. And actually, I hadn't thought of it, but there is a precursor to this, and it's in a mine in Minnesota. So up right at the Minnesota-Canada border, I don't know if any of you have read about that, you can go down a mine shaft half a mile underground, and the mine elevator and shaft is as it was in like the 50s. And they take school groups down. I'm really impressed, actually. You go down for 4 minutes with your miner's helmet on in the complete darkness, and you get to the bottom and you open, the rusty steel door, and you see this huge cavern which has a big, in this case, lots and lots of huge sheets of iron, which are detecting these particles that are coming from the beam at Fermilab, and also, of course, all the particles you don't really want to see that come from the atmosphere and all around. So there's been a whole program of these experiments. So yes, there's also the muon program, another kind of particle, and there was another big press event last year when a big magnet was moved from Long Island to Illinois, and it had to go on a barge down the east coast, and it's huge. I mean, about as big as across, it's almost as across as this room, not quite. And it couldn't move more than a millimeter. And so they had to have all these gyroscopes and suspension on this lorry that was carrying it so that the whole thing wouldn't move a millimeter. Had to get off the jetty onto the barge on Long Island, had to go all the way down the coast, all the way up the Mississippi, or I think it was another river, and then it had to come through the tollways in Illinois at night. So there's some nice pictures of it in Costco's parking lot in Long Island. So that is being used to look for a different particle than the neutrino at Fermilab in some new experiments. So dark energy, we're a leader in that. We have a telescope in Chile. Of course, we're always collaborating with a lot of other labs and a lot of other universities. There's never a experiment in high energy physics. It's just one institution anymore. And so that actually gets into the news at the moment because it's been doing some maps of very, very distant galaxies and large-scale structure of the universe that is very near. Okay, so, scientific computing. So computing, your computers, our computers, underpins all the science and discoveries that are done. So we have quite large computing facilities, rooms of racks and racks of computers and disks, and we have big take robots at Fermilab. And of course we rely on very high-speed internet and networks to move the data around between the institution that is collecting the data and all the institutions that have the research institutions that are actually analyzing it and producing the discoveries. We at Fermilab, our computing does support the Large Hadron Collider program in Switzerland. We are the top computing facility outside of CERN for one of the big experiments there. There are 2 huge experiments and then 2 smaller experiments. We support all the computing that is done to actually analyze the data, to look at the statistics from the data. One of the things about high-energy particle physics is that you really have to look at the errors. You have to understand all the standard deviations, all the random errors that are happening, so you spend as much computing, if not more, trying to understand whether the results you're getting are correct, whether you can validate and trust the answers you're getting from the very complex programs. The programs are million-line C++ codes, and they're specific for an experiment. So the million-line codes for CMS are different than the million-line codes for Atlas, which is where the US facility base is in Long Island at Brookhaven. And whereas astrophysics is different, and one of the things when we joined the astrophysics experiment was that, you know, if you see a point in the sky, that may be a discovery. You don't care whether the point is this big or that big or the other, it's just there. In particle physics, the errors are everything. So we support the neutrino programs, and we also support the Cosmic Frontier, the astrophysics programs, but we also do modeling of accelerators. Accelerators are extremely expensive, difficult to build pieces of equipment. They have hundreds of thousands of components. I have another slide on that. And modeling them and understanding them both before you build them and then do all the engineering, and after you build them when they're not actually working properly is very important. Lots of computing for that. In fact, we actually get tour people coming from the nuclear power industry. And so they do a lot of modeling for their systems because they're looking to check that it's safe, they inject errors. I think that the modeling they do is somewhat similar to the stuff we do for accelerator modeling. We also do theoretical physics, try to predict what the experiments might see and also to explain what the experiments see in terms of the theories. So, the principles of scientific computing for particle physics that I feel we follow are that we want it as cheap as possible, of course, because we have huge amounts of computing. We're using hundreds of thousands of computers. We are having, 10 to 100 petabytes of data, which is, 1,000 to 2,000 what you have on the biggest of these thumb drives now. There are many, many people. So both the LHC experiments have, 2,000 to 3,000 physicists working on them. The smaller experiments, like my husband's, have about 100 physicists working on them, and they're all working together to get the result, find the Higgs. They're working on other things as well, but there's a main thrust always of the group. We use open source software. We hate paying money for software because we can write it better ourselves, or out there the community can write it better themselves. So we used to write operating systems, but we were actually an early adopter of the Linux operating system in the US. As an example, as I said, we use C++ as a coding language. Used to be Fortran, now it's very much C++, so we've actually contributed to the C++ standard for the last year when there were some changes, and Python, which is a scripting language like Shell. And we don't need supercomputers in the main. You see lots of things in the news and technical magazines about building exascale and petaflops and these big machines at the other DOE national labs, and the National Science Foundation has got this Blue Waters machine at the University of Illinois in Urbana-Champaign. In the main, physicists don't use supercomputers. We just use ordinary computers, many, many of them. And the reason we do that is much, much cheaper. And our software can run on it. And as I said, it's collaborative. Now, I may have forgotten some. If there's anything you think of or you have a question about, please don't hesitate to ask. I've told there's questions at the end. I'll try and hurry up. And this is my boss, but I wrote that slide. Okay, so yes, so the exception to the rule, there's always an exception to the rule, is that we need supercomputers for modeling, and that's because we have so much data and the components of the accelerator, when you're actually coding them in software and trying to emulate what they are doing, they actually have to interact, and so you need supercomputers. We can come back to that. Okay, so the computing stack, and I'm sorry that bottom one is difficult to read. So we start off doing R&D. We do quite a lot of research and development into software and computing at Fermilab because our needs are very much in the front. I mean, the High-Energy Physics has been very big collaborations for decades, for 30 or 40 years. And we've always known that software and computing is absolutely critical for getting the results out. And so we've always self-funded in some way doing the computing. We are not expecting to contract it to other people. We're not we don't forget about it like the Sloan Digital Sky Survey did. And so we regard, you know, if you've trained in physics, you've trained a computer expert, which, you know, is ridiculous really, but that's what you think. And so we do R&D and research for adapting and developing products for scientific software. Then we have these computing facilities that I mentioned before, and I'll talk about in a bit more detail of the networks of computing and the disks and the tapes. And then we have the science operations and workflows. We develop the actual software for the experiment and the project to run on the facility and provide operations support. And that's a huge endeavor. And we're, you know, they say that bioinformatics and climate are going to have these needs, they're going to have this amount of data, and it's been a long time coming. Nowadays, because sequencing machines for genomics are so cheap, every lab is having one, the aggregate is a huge amount of data. But for particle physics, we are talking about petabytes of data for each experiment. So, networks. We have about 35,000 network ports, spigots into the computers. We run all different speeds of networking, 100 gigabit, we actually at 1,000 gigabit now, and so we're right at the forefront of doing networking research. In fact, till recently we had a dedicated network line under the ocean, under the Atlantic, between us and Switzerland for getting the data out from CERN and bringing it to the US. So I have a slide where you can't actually see what's written. We have high-speed data caches. So you have a disk on your computer, you're using remote disks through Dropbox and Google and things like that. And we, in order to get the input-output to the software programs, the executables that are running, we have huge amounts of disk caches, just racks of them sitting in our computing center. So I don't know if the tour to Fermilab's going to the Grid Computing Center, but we basically have 3 warehouse rooms. Each one's probably a quarter of the size, so the whole thing's this size, in an old experimental hall. Where, as I say, we have these racks, and then we have lots of cold air blowing, and we have bits of plastic hanging down so that we keep the cold air contained into the computers, and all these racks of disks that people use and put their information. And then high-energy physics still use tape. So many domains, many scientific domains, don't use your physical, you know, take a cartridge out and move your data around. But it's still cheaper than disk, and it's really quite reliable. With this, you have to worry over the long term, and experiments are decades endeavors, whether it's going to last. So we actually have 3 big Oracle or TK robots that are sitting in our computer center, when we have these automatic, you know, things that move around and take the tapes in and out. The first robot I saw is actually a dry cleaning place in Oxford in England in the 70s. I was very impressed by this, but now it's reused for actually science. And so you have racks and racks of them, and all the data from Switzerland is put, for the CMS experiment, one of the experiments is put on tape here, and we actually keep the data for 30 years. We have to change technology every 5 years, so we have to copy all the data off one tape and onto another tape. We have to check that things aren't breaking. We've had a problem of bugs actually last year, real, you know, flying bugs, not software bugs, that have actually got through because it's a prairie. Fermilab is a big prairie. This is an experimental hall, you know. So it's repurposed for computing, and somehow there were some little flies getting through the vents. Now it's not clear whether all the problems we're having is from those, because Oracle is saying, oh, well, some of the metal from the heads that read the tape is coming off because we use them so much. But anyway, this is a big deal. And we regard ourselves actually as a premier data archiving facility. We're starting to offer that service to other sciences in the States. And another one, so yes, we have 76,000 computers. They are like your laptop. They are what we call pizza boxes, right? You just shove them into a rack. You have to worry about how much power you're using. The big issue now with computers is how much electricity you're using. And we not only use computers at Fermilab for our scientific computing and software executions, we're using computers around the world, and I'll tell you about that. So, computing for high energy physics is sort of a recap, consists of, you have the big detectors with all the electronics on, with the beam running through them, either through the middle, or from the top to the bottom, or from the bottom to the top. And you need to write software and have computers to acquire and store the data. You need to produce simulated data to compare to the data you're acquiring, because you need to understand the systematics and the errors that you're seeing. You need to say, am I seeing what I predict? And if not, why not? Then you need to process it, which means you have this huge, huge volume of data, and you want to translate it into physics quantities, into the scientific quantities that will actually tell you what you've discovered, and then you need to analyze it again and again in order to get your one discovery at the end, your Higgs. As I say, get physics at the bottom. So there are millions of channels of data collected and stored. We're talking about millions of these things. There are petabytes, or back in the 90s we said we actually had an Eiffel Tower of CDs of data coming from the Tevatron. Now, of course, CDs are bigger than they were in the 80s, but we have 10 times as much data. So we're talking about things that are huge. And millions of CPU hours, so 100,000 computers around the world for the Large Hadron Collider. And as I said, not as supercomputers, but traditional PCs and pizza boxes. So I'm sort of worried a bit around time. So there's digital electronics and data acquisition. We do a lot of work there. We're starting to adapt that for the model of the Internet of Things, which means that everything you pick up anywhere has a chip in it, and so is on the network and doing computing with a lot of scale. There's an emphasis at Fermilab now that when we're doing research, when we're doing development, we do try to think how it can be applied to other sciences, or to industry, or to society and the public. As I said, the simulation, large-scale simulation of the detectors. You can see the CMS detector there. There are hundreds of hits of as I said, 1 million channels that come out, and we have to try to reconstruct the path of all these particles, of all these fundamental particles, in order to understand the science behind it. So we need to find out where the vertex is, where the particles actually collided, very, very, very accurately. And you have to understand from the sea of points over on the right at the top where your actual tracks are. We call them tracks of the particles coming out from the interaction. The tracks that are coming from the cosmic rays that we need to throw away, tracks that are coming from beam particles that actually didn't interact but interfere. So there's a lot of track finding, vertex finding. We put magnetic fields on. You have to, in software, in your computer software programs, understand how the electrons or the protons or the lambdas or the muons will bend, given that there's a magnetic field there. And that helps you determine what particle they are and what mass they are and how fast they go. We are not only using the standard PC now, but we're starting to use all these graphic processors that are coming on the Game Boys, which are called GPUs. I should have explained the acronym. So they are fast for particular pieces of software. So you can't put your whole physics program on it. You can put a specific piece which is tuned to the kind of hardware or computer chip that is in a graphic processing unit. But then you have to get the data to it, you have to get the data out of it, you have to worry about how much memory you need, and so there's a lot of tuning and configuring of all the different pieces and parameters to get your the best throughput, your most effective throughput. And of course, since we have so much computing and it goes on for so long and we spend so much money on it, it's worth investing in understanding how we can do it most efficiently and most cheaply. So as I said, we store data on tape. We have over 50 petabytes on tape. We have room for about 300 on our tape systems. We have to really worry about getting data in and out. and we have to store it sensibly so that you can get it out very quickly, because of course it's a write once, read many times systems. Most tape archival systems are write it and hope you never have to read it because it's a backup of your disk. But in physics, you're reading your tapes all the time because you can't afford enough disk to put it all on by your computers. As I said, we're starting to have a partnership project where we can do work for others and store data for other scientific domains. And so we've got some biology data there, and we're working with the neutrino experiment at the University of Wisconsin to put their data on. And then we just have a pilot with the Simons Institute in New York City to put some of their genomic data on our tapes. Operating systems, as I said, we used to really care about them and felt we needed to tweak them, and we used to find problems with them when we actually used them for physics. And we actually are, as I said, an early adopter of the use of the Linux operating system. And we actually package, distribute, and support something called Scientific Linux, which we then provide to researchers around the world. And sometimes we get to do it quicker than some of the regular Linux packaging people like Ubuntu or Red Hat. And so we get a lot of downloads for that. When we actually tell the city of Chicago, the benefits of Fermilab, Scientific Linux is always one of the things we say. We don't say we found the Higgs. As I said, large-scale collaborative tools, we're an early adopter of the web. Big data, another buzzword out there now. So big data means different things to different people. They're just asking me to be the interim project manager for big data at Fermilab, and my son, who works in geographic information systems for engineering, mapping out power lines and toll booths and stuff, told me it's validity, volume, variety, and something else is what big data is. But these are techniques where you move the computing close to the data, and then your analysis can go faster. So what we do at the moment is we tend to distribute our data around the world to the computers that are sitting at the universities, at the different laboratories, and do the computing there. But here, you add the data itself, you have it, you say, okay, let's put the computers near them on the network. And so we're looking at how we use this in high-energy physics. Okay, researcher analysis tools. So we have a high-energy physics-wide analysis package, which is now being used by medical physics, by astronomy, and some other science domains, where you actually create histograms. So physics is a statistical science. You're never really looking at one event and saying, okay, you get millions of events, and you actually do the distribution of what the mass of these tracks is, what the mass of the particles are, in order to be able to determine a result. And you always say, I think this is the answer to within this accuracy, or this statistical validity. And so we draw a lot of histograms. We're not actually a very visual 3D science like astronomy. Astronomy, as I say, you just show a picture of a galaxy and you found something. So in particle physics, you have to troll through your petabytes of data again and again, put different cuts on, different criteria for saying whether this is real science or it's just garbage that's come into your detector by mistake, in order to get the answers. There's a lot of software done and a lot of computers executing programs to do that. So, as I said, it's a collaborative science, and one of the latest papers that came out in Nature is a paper that has the most authors on ever. And the top line says it's a physics paper with 5,000 authors and 5,000 physicists. I mean, it doesn't count the engineers and the technicians and the computing professionals who contributed to it. And this is a combined paper from the two big experiments at CERN. So it's a big deal. You know, experiments really are in competition with each other. But this is such an expensive science, and there's so few big results, that in the last few decades we've started to try to combine results. And that's an extremely difficult thing to do, because as I said, a lot of the validity of the data depends on how well you understand the error conditions, how well you understand all the electronics that's taking the data in the first place. And of course, experiments they build different pieces of hardware, so they are different in that way. We have software frameworks. As I said, I tend to work much more in the software part and the programming part of scientific computing than in the hardware part, and so I try to emphasize that a bit more. We have these big frameworks in C++ that everybody is using, which are generally applicable to different experiments. And they do things like building your executable, getting your data in and out, understanding what configuration parameters you used, what operating system version you used. I mean, we have found that when you go from one version of an operating system into another, your results change in physics. And you have to understand that, because you have to understand it to a very, very great level of detail. So the provenance is all the information that told you what the situation or the environment in which you were running your program. All right, we do distributed data processing. As I said, we send physics data to remote universities and collaborators over the internet. And we are a leading contributor to the Open Science Grid, and I was the executive director of the Open Science Grid for 6 years, and now I'm chair of the governing council. And we have, as part of the collaboration, 6 DOE labs and over 100 universities in the US who are prepared to allow their computers to be shared by different science codes over the internet. Now, I don't have a slide on security, and you mentioned it before, you know, protect your computers, they're after you. Of course, Department of Energy labs are a target of opportunity for people trying to break into computers. So we have quite a big security team. We really do care about it. We have a large number, we have about 50 computers we call our tar pit. And our tar pit is supposed to be attractive to those hackers. So if, you know, we're being scanned all the time, you know, there's thousands of people trying to break in every day, but we say, come on, yeah, you can think you've got in, right? But you haven't. But do come back, because then we can try and track you. Or do come back, but we're not going to answer you for half an hour. And while you're waiting for that answer, you can't be trying to hack anybody else. So that was at the beginning, that was quite good. It's go very slow, right? And yet we're trying to do science that's open to the world. We've got to not put barriers in the path of the scientists and the researchers that are doing things. And we have researchers from all over. So we do a lot of scanning, a lot of interpretation of the data, of course, and we do care about security, but we're trying to say that we're an open facility, an open science. So it's a big deal when you get 100 universities saying, okay, we're going to put software on our computers that allows other people to come and use them for science. And of course, science is, you know, people are doing strange things, you know, they're going to be changing their programs every day, and who knows what they're going to be doing. So as I say, we in OSG have about 100 universities. This is the first time that Fermilab computers have been used to run bioinformatics or genomics or climate codes on our computers when it's not being used for physics. Right. And we are part of a worldwide distributed facility which is used for the Large Hadron Collider. Joe was asking me about, you know, the person in the office next door who was running one of these at-home applications where programs are distributed to your personal computer and you can allow it to run science code to look for extraterrestrial life, or for, in the case of LIGO, you can look for gravitational waves. That's one of the big experiments at the moment. And yes, that's what it's kind of like for all these science codes. And what we do is you don't actually have to pay for it. Since DOE and NSF are paying for all the computers, you know, an individual researcher doesn't have to pay for the computing that you're using. So I just wanted to finish with a bit more about distributed computing because, again, clouds, grid, clouds have been in the news as buzzwords. So the grid was groups of users who were trusted by all these different computing systems, and you can get an allocation on it, but then you can have opportunistically, you can use pieces of the computers that are not being used by the people who own them. Then the cloud. So the cloud is distributed computing. You can have the difference in my mind between a cloud and a grid is a cloud has one spigot to go in and out, and then all the different kinds of computing are behind it. Whereas in the grid, it's kind of democratic. Every university cluster, every lab cluster has its own port onto the grid and has control over their own computing and their own disks and who runs on them. With a cloud, you just go through one pipe and then you have all these different resources. And the biggest clouds, of course, are commercial now. So Amazon Cloud, Google Cloud, Microsoft Cloud are big names, big facilities, and they're going after the scientific market. And in particular for Amazon, they have something called the spot market on their cloud. So if other people are not using the computers, then they will sell off the computing they have available cheap. And it's still 5 times as much per physics output as having our own computers and using university computers. But 5 times is not that much, it's getting there. It used to be, 10 or 100 times as expensive. So Amazon actually is growing a scientific group, and they're going around all the experiments, high energy physics, particle physics, ocean, the big ocean observatory has a contract with Amazon to get their business. And it's a business case, they're not doing it because they think we're cool. Oh, and the last thing is HPC, and I should have spelled it out. That's high performance computing. That is the computing. That is the supercomputers. Now, because supercomputing is political in some way, we have the America's competitiveness is, do we have a bigger supercomputer than Japan or China or Europe? And China built, this very big supercomputer. Congress does tend to fund supercomputers. And they're just funding a big new exascale supercomputer through Department of Energy, which will be at Argonne National Lab in Illinois and at Oak Ridge in Tennessee. And because it's going to be there, they're getting more money, and so we think, and physicists know how to use computers, so we're going to try and use them and get some computing that is free for our field. But actually using supercomputers, because they're very expensive, you actually have to present what you're going to do, the science you're going to do, to a committee, and they take a decision as whether they'll let you on or not. Whereas in our model of grids and sharing of computers, basically we let any science research that has been funded, and so they've already passed some peer review, we allow them to use our computing. And actually that is my last slide. So now I'm available for questions, and we'll see if I can answer them.
Here, in your slide on neutrinos, it said neutrinos oscillate, thus mass, but I don't know that corollary. Photons oscillate. I don't believe they have mass. I mean,
in terms of oscillate, they don't change into different photons. They're still a photon. So I think it's a definition of oscillation.
Okay, yeah.
Right?
I have to grant you that.
I actually think oscillation is a strange word for the neutrinos because, yeah, exactly. The traditional oscillation is something going up and down, not changing its whole character and nature. So I think it's, personally, I find it a confusing terminology. Yeah, that's right, metamorphosis is better. Yeah, I actually have a microphone, I just have to point to it. So I actually, in some of my spare time, am trying to help with the education and outreach. And the way that they try to demonstrate what oscillations of neutrino means is they have these multicolored little toys where you flip it and it changes color, you flip it, because on a different kind of the triangle are different colors. But yeah, it changes nature. Right. Yes.
I've forgotten, but do you compare or contrast the Tevatron at your facility on CERN Hadron Super Collider?
So the Tevatron, the Super Collider is some factor higher energy than the Tevatron, do I remember what, and higher intensity beams. So it's bigger, the circle is bigger, and how much? So I would say 10 times, but I'm probably wrong. You can't trust me with numbers, Mike. And I don't have it on my cheat sheet. But the Tevatron is 4 kilometers in diameter, and the Large Hadron Collider is about 20 kilometers in diameter. But the Tevatron is colliding protons and antiprotons, and the Large Hadron Collider is colliding protons on protons. So maybe someone here knows the answer better than I do. But a fact, I mean, it's not 100 and it's not 2. Okay.
I have heard that there were a lot of budget cuts at Fermilab. Can you discuss where the budget cuts were and how did it affect Fermilab?
So the budget cuts, 5 years ago there were over 2,000 employees and now there's 1,700. Some of the experiments have not happened, like there was an experiment called BTEV, I mean it's just names, and the Tevatron was closed down and we're not building a new Tevatron. What we're doing is we're turning there used to be enough money in the field globally that you could have 2 accelerators doing the same science. Now there isn't. Now the whole community, which already worked internationally, but we get together to discuss internationally a program where one country will build an accelerator to do A and another will build an accelerator to do B, rather than having everybody do A and B. So that's why we've moved from being what's called energy physics, which are these big accelerators, to focusing on neutrino physics, which is intensity physics.
I have a question. Where does the neutrino get the energy to travel through the Earth? I don't understand. It could go completely through the planet and not be affected?
Yes, but remember, most of stuff is empty.
Oh.
When you drill down and you magnify your table and your chair and your us, most of it is empty space, nothing there.
And the difference between dark energy and
Dark matter.
dark matter,
Right.
is there...
So they're really nothing to do with each other. It's extremely confusing, in my opinion, to call them both dark X. Now the reason people call them dark X, where X is matter or energy, is that we haven't detected it before. And we don't know how to detect it. And that's all it means, right? It's not light, we haven't seen it, right? It's dark, it's unknown. It's not a fundamental property of nature that it's called dark.
I have one other question.
Yeah.
How did liquid argon have a program containing liquid argon? I don't understand the thing. And National Geographic said that if you took all of the empty space on the planet Earth, it would be the size of a golf ball. Is that true?
I don't know whether that's true. I'll go and look that up. I mean, take all the empty space. Okay, but I want to answer the liquid argon because, of course, you know, it's a family thing. It's an inert gas. So one of the problems of physics is because you care about it's so precise and you have to understand all the errors, is that radiation, the natural radiation that's in the earth, that's in everything, can confuse you. You'll detect it. So if you have an atom that is actually giving off alpha particles or electrons or something, you'll detect it. So you want an inert element. And so you have helium and you have argon and you have something else, right? And it turns out, and xenon is another one. And then now there are xenon detectors. And so people, if you can see something hit something in liquid argon, you see things because they collide, but they're very, very small, so most of the time they don't collide. They go through all this empty space. And that's why neutrinos can go through the Earth. They're very, very small. They don't have a magnetic charge. They don't have an electric charge, so they're not attracted or deflected from atoms or ions. Or the negative electron and the positive proton, they're not attracted to them. So they just go through most of matter without interacting.
Dave, could you do the last question?
Yes.
Okay, you mentioned that your lab operates all the time. CERN just recently announced they were coming back up with their collider for the next 3 years.
Right.
Is there a predictable downtime for your unit?
Yes, so we're in a downtime of some of the accelerators today, but we're in an uptime for other experiments, because some of our experiments are just looking at the cosmos, which is there all the time. And we have several different accelerators, and we can turn them off individually. So yes, we do have downtimes.
Ruth, we'd like to thank you very much for a great presentation. Got about 3 more things to go over before we break up. They're very quick. I have to apologize for the fact that we had 2 blank slides on the community matters. Somehow the pictures didn't translate through. I don't have the details, but you can see it in lifestyle. The one slide was talking about tomorrow. Prairie Singers have their 2nd concert, and the other slide was about the theater company. Will be having their play in August, and in June they're going to be starting to sell tickets for that.
George, it's Strutters tomorrow.
What?
Strutters tomorrow at the high school.
Oh, it's at the high school tomorrow.
Strutters.
Oh, the Strutters, I'm sorry. Wrong one. Without a slide, I'm in trouble. I also wanted to mention something that's come up that before everyone leaves. There's an issue on Windows 10. A lot of you have been seeing icons popping up on your computers. Download Windows 10. You can do that. There's a program, it's free, depending on what software you're operating from. But the official position of the club is you might want to wait a few weeks and see how Windows 10 works before you jump head on into that. The other thing that I wanted to mention is more from a personal point of view. I've been president for 3 years. I'd like to thank the board, the members, the monitors, and everybody who has made this club a great club and has helped me for the last 3 years. Without their help, this wouldn't work. And so I had a good 3 years. I enjoyed it, and I'm turning it over to Frank. So take care and have a great day.